No, you don't need to dress nice. Wear regular clothes. Okay. Day 13, I think we're wrapping up spectroscopy here.
Mine says 12.
Yeah, no, it's a typo. It's a typo. Okay. Common ideas and terms. Slit width. Slit width. Okay. Oh, Ricky, what is slit width?
No, that's like the width of that slit.
Yes?
The selected wavelength passes through.
Yes. What's the word for that little piece of equipment? That's monochromator. Right. Monochromator has how many slits, Emily? Two. An incoming from the source and then an outgoing, right? Okay, so does it seem like, Sandy, that slit width is something to keep in constant during a quantitative analysis? Why? Why? Does anybody know why? Mathematically why? Because that's calibration curves. Quantitation is all about numbers, right?
It's like what you told us yesterday with our samples. If we change it, then we might not get the same readings for each sample. Same matrix.
Well, how does it have to do with matrix?
You should just factor into the equation, right? By doing that.
Not really a new factor.
Aren't you just trying to get one wavelength?
What is a, if you're going to do a quantitative analysis, you're plotting absorbance versus,
Wavelength?
making calibration curve, absorbance is your signal, plot it versus concentration, right, of your analyte. Okay. Now, if you change the slit width, has nothing to do with the concentration of the analyte, right? That's just a number that you're going to end up with. That's your answer. But the absorbance measurement, what is absorbance? It was negative log of transmittance, right? And transmittance is what over what? P over P. You change the slit width all of a sudden. What did you just change? Depends on which slit you messed with, right? If you messed, I guess either one is going to, I guess if you make the slit wider, you're going to be increasing this intensity, right? Make it narrower, you're going to be decreasing it. So you got to keep it constant. Otherwise, you're going to get different absorbance readings for the exact same concentration. Okay, does that make sense? Yeah. So it's not really a new factor. It's kind of messing with the old ones. Rico, what is this? You ready?
Be the C word.
Yeah, that's the cuvette. Pass it around. Okay, Adriana, you've probably seen a cuvette. What does a cuvette have to do with an absorbance measurement mathematically?
Oh, from Beer's law.
Oh, yeah, it's the path length.
Yes, with little symbol what?
The E?
Not C was the constant.
No, B.
B. There it is. There's the slit width. All right. All right. Sorry, not slit width. The path length. Okay. So if we
That's the B. That's EBC.
yeah, EBC, molar extinction coefficient times the path length times the concentration. Okay. Beer's law, just like McGee was mentioning, indicate whether the following increases, decreases, or has no effect on an absorption measurement. So just imagine this is, you're putting in your little cuvette in this little Spec 20 here, right? Measuring and getting an absorbance measurement, some wavelengths. You have it set up, and you're just popping the cuvette in and out of there. And I guess, Ricky, you weren't so careful. You got fingerprints on the little cuvette that's being passed around. What would be the effect on your absorbance measurement?
You would raise the absorbance.
Yeah. Everybody agree?
Yeah.
Yeah. Because yeah, exactly. It's mathematically. Now it doesn't affect, right? Okay. trick question. How about, let's go back to fingerprints on a cuvette. Right? He's right. Right? We're all thinking the same thing. All of a sudden, you grab the cuvette, put your fingerprints on it, and put it in there. Right? What if that cuvette had fingerprints on it from the very first second you went in lab? And you're holding it correctly, but there's a big bloody fingerprint on there. Yeah, it's bloody even, right? Would that affect your absorbance measurement?
Does it depend on the blank?
The blank cancels it out, right? As long as you put that cuvette in, and those slots are really reproducible. That cuvette's going to slide in the exact same position every time. So that fingerprint was there from the beginning. It's going to get blocked out by your background, right? Because it was in there for the background. So as long as so pretty much we need more English to describe fingerprints on the cuvette, absorbance reading going up. It has to be kind of what's not said. New fingerprints, right? That all of a sudden you just grabbed it and then you put it in there. Right? You grabbed the cuvette wrong. So I think that's how all these questions are really supposed to be read. That this is just something you all of a sudden did, right? You already made the calibration curve, you did everything. Now you're just after an absorbance measurement of your unknown. You're just plopping it in the cuvette and then putting it in the instrument. Now you put some bubbles on the cuvette. Randy, what do you think would be the result on the absorbance measurement there? There's bubbles. Well, on or in, right? Probably in would be a better word than on. Well, I guess on is right too, because they're kind of stuck to the inside there. She says decrease. Then she says no change.
And then she said, I'm going with decrease.
Decrease? Why decrease?
Because then it's just an empty space.
See that? Because if you say decrease, you're arguing that the path length what? Is effectively decreased, right? That's the argument. I'm not saying it's right, but that's the argument. And it makes total sense.
Then you're just going
right?
air and then a little bit of the thing,
Yeah.
air and then a little bit of the
The
thing.
problem, this is the problem with it.
What if you were like,
Anna, can you see a bubble? Can you see a bubble? You know, there's a bubble in the cuvette. Can you see it? Yeah, otherwise you wouldn't know there's a bubble there, right? Why can you see the bubble?
because it's there.
Why can you see it?
Because my eyes work.
The bubble has to be doing this, otherwise you couldn't see it.
Oh, the fresh
Has to be-
stuff.
Which word?
Refract. No,
Isn't it reflective?
Reflecting. It's reflecting the light. It looks like a mirror, doesn't it? It looks silvery. It's reflecting everything. So it's not letting the light get through. It's like a big black hunk of dirt in there.
So that would actually
So it actually
increases.
increases the absorbance measurement.
Holy.
You pretty much have to actually do it to believe it. Okay, but it does. The cuvette is incorrectly positioned, Robert.
Okay. how
Yeah,
would you
okay,
make a
good
square?
question. How would you give him the cuvette?
There's one side.
Where's the cuvette?
There's one side that's more transparent than the other, though.
well, this cuvette doesn't, oh yeah, it does.
Yeah, does it have a little
One side's dull and one side's
Yeah.
shiny.
Okay.
It's incorrectly positioned. Now, it's square, so you're right in the sense, how can you put it in wrong,
Yeah.
right? But let's say this is the bottom of it, the cell holder. What if you just jam it in this far? That's incorrect. That's what I really meant by saying incorrectly positioned. Right? I mean, I guess the other way you could think of it as, oh, it's shining through the frosty sides. That's kind of incorrectly positioned. So there's two. I think there's only really two ways to do incorrectly positioned, right? If the light's going through here, striking Pablo, and you do the frosty side part, okay, that would increase it. What if you're going to do it right, but now I only jam it in? Don't
So
jam
now
it in
am I
all the
shining
way.
through here, or because that would depend on where I'm shining through. If it's the skinnier part down here, then wouldn't that decrease it?
All right. Incorrectly positioned. Now think about it. Right? If the light's going here, or whether it's going here,
That's the same thing.
yeah, it really doesn't matter, right? But what if it's incorrectly positioned so that now it's here and the rest is down here? In fact, the number, you pull the cuvette out of the holder, the number goes to,
Negative.
Negative.
Or should go to 0.
it should go to 0. Why?
Because you did the blank.
Because the blank and the transmitted, or the attenuated, whoever was after that T word, right? They're the same thing. What's a negative log of, what's a log of 1? 0. So that's why it should be reading 0 if you did your background right. Okay? If you pull everything out of there. So this guy, so there's two answers, I guess, for incorrectly positioned. One, it's going through the frosty sides. That would increase it. The other one is, if it's incorrectly positioned, right, incorrect. So that means that only part of it's going through the cuvette. The rest is just shining through the bottom. The absorbance measurement would, well, part of it's still going through, but the rest is just, yeah, the absorbance measurement
And even if it was 0, that would still be a decrease.
decreases. Right? So going through the frosty part, the absorbance measurement increases, right? And if it's not correctly positioned, not jamming it all the way down, it decreases, right? Okay. How about not enough solution in the cuvette? Ashley, how about that one? Not enough solution in the cuvette. So you have to make it a problem because there's not enough solution in the cuvette. Because if you didn't fill up the cuvette all the way to the top, but it's still shining through, that's not a problem. That's not enough solution in the cuvette. See what I mean? Not enough solution in the cuvette means, I don't know, the light's, yeah, it's not even passing through. Oh, it's either it's not passing through, only passing through partially. Same as the incorrectly positioned idea. So the absorbance measurement should decrease. Right? There's not enough solution. How about scratches on the cuvette? Emily. Yeah, it scatters light. As long as the same cuvette wasn't used for the background. Right. Okay. Single and double beam spectrophotometers. What?
Scratches have to be on the not frosty side?
Yeah, they have to be on the not frosty side too. That's very, very true. All right? Okay. What is the physical difference between a single beam and a double beam spectrophotometer? So here they are. Which one is which, Sandy?
Don't worry, you will.
Which one is which?
And it says mono.
Which one is which, Sandy? Single beam and double beam. Top is the single, bottom is the double. Good. Okay. What's the difference then? What could you say is the difference there, John? I mean, look at all the little pieces there. Does one have 2 monochromators or something? No. So what is think of it this way. Let's back up a little bit. If you were going to have your little cuvette here, and you want to get the absorbance reading at 220 nanometers, or 400 nanometers, whatever, right? Pick one. How would you do that reading with the single beam spectrophotometer? How would you do it? Okay, so select the little wavelength that you want. Put your sample in the cuvette. Yeah, it ain't gonna work. You only got half of your absorbance readings that way. See what I'm saying? Because absorbance is negative log. What is it? P naught over P or? I forget this whole. Right? Isn't it P over P naught?
That'd be Poe.
But either way, the point is, if you fill your cuvette and pop it in the single beam, you just got which reading? You're getting the intensity through there. You just got P. You forgot about P naught. You gotta care. So what do you have to do
I would assume
first?
that you did the blank already.
You can't. I asked, how would you do it? So again, how would you do an absorbance reading using the single beam spectrophotometer? What do you have to do first? I like the dial thing. Get it to the wavelength. Good. Do that. Or push the button, whatever you got. To get it to the nanometers. Then do what? How do you get your blank?
You just put the regular keypad in with that.
Yeah, you can put the regular cuvette in, right? Without anything, or with water, right? Whatever you want. Okay. Then you push background or whatever, right? Whatever the little button says. Now you're ready for Rob's step. Dump it out, put in your sample, put it in, push the absorbance reading, right? Because it's going to remember what the incident was. It'll figure out what the transmitted intensity is and calculate it, right? Okay, Adriana, how would you get an absorbance reading for a double beam spectrophotometer? What would you go about doing?
The meme-worthy face that she made.
Now, in the single beam, here's where you put your little cuvette, right? Where do you put your cuvette in the double beam?
Where it says sample?
Where it says sample. Well, what's the other one for then?
Oh, that's like what we have upstairs. Yeah.
But it's not a blank, it's more like
A reference?
Okay.
What is that?
Your blank. Yeah, your reference cell can be your blank,
Yeah.
right?
So that's
And
what
then
we
you
do.
put your sample. So how many cuvettes do you? It looks like there's spots for 2 cuvettes. So the double beam is doing what, Pavel, simultaneously?
It's reading.
It's reading.
Yeah, it's reading both.
Is reading what? What's
PO and
the PO and the P simultaneously. Okay. It's reading the transmitted and the incident simultaneously.
Let's actually see if it is before
Okay.
or after.
So Dr. Smith, like when it comes out,
It
it's
is
gonna
proposed.
come out with both.
Oh, it is before. It is before.
Now,
I just meant
Real-
PO.
realize we're just talking about one absorbance measurement, right? Absorbance versus wavelength. We're talking about one dot, right? If you want more absorbance readings, you have to, scan it. Scan the monochrometer.
The reference cell isn't the one that's gonna show up then.
The reference cell has you can just put your blank cuvette in there, right? And then your sample, you're going to have your sample in there, right?
Was there a P not before?
Okay. And then you see the work that it would take to get an entire absorbance spectrum using a single beam. Look at all the individual points you'd have to get, right?
It just does it
Because-
for you.
Because you need to get an incident intensity at each single wavelength there, right? So you have to be popping out cuvettes the whole time. Does that make sense? Whereas versus this one, you just put them in there and let it run. So we paid about 20 grand more to get a double beam. Now, why is it advantageous over single beam?
That's where it works.
You don't have to do all that work. That's true. But I don't care. You guys are students. You don't get paid per the hour. We could have saved 20 grand. That's not the reason why.
Minimize error
What? There's a lot of air. Where?
in the keypad.
The problem is your light source, and especially your detector, their sensitivities and their efficiencies, their abilities to work change with temperature, change with time. When you first pop on a lamp, man, and you actually see this in the AA. It takes about 5-10 minutes for the intensity just to kind of level out. Is there a warm-up time for a double beam spectrophotometer? No, you just start using it right away because it's measuring transmitted and incident at the exact same time. We don't care. We don't care how warm up the detector is. We don't care if the light source is behaving or not. It can even, I guess, flickering wouldn't be the best thing, but it really wouldn't hurt anything because it can't. Right? It's measuring transmitted and an incident at the same time. Okay, that's the real reason. It reduces the error. Okay. So you're in you're doing any absorbance reading. I don't care if it's using the FTIR, it's using the AA, and this happened with the AA in one group, or the UV vis, you get a negative reading when you start doing your lab, your analysis. All right? So is that garbage, your Andy, or does it actually mean something?
We get a negative?
Yeah, you get a negative absorbance reading. Negative 0.12. What just happened? Is it garbage? Things aren't behaving? Machine needs to turn everything off, turn it all back on again? Will that solve it?
No, you have to.
Rerun it? Maybe play with the lamp and get it optimized? The math tells you. How can you get a negative absorbance reading?
You get a smaller number for the PPO.
There you go. When the P, this P, because we like and we're comfortable with positive absorbance readings. That means P is what, bigger or smaller than PO? How do how do P and PO compare? P has to be, P is the light that gets through the sample. P naught is the incident intensity. They're both intensity measurements. P has to be bigger than P naught? Which one is the incident intensity? P naught, PO, right? That has to be bigger, right? Because it's the incident. It's the light striking it. If it absorbs anything, it attenuates the light, so P would have to be smaller. That makes sense? If the sample doesn't absorb anything, P and P naught are exactly the same. Then you get absorbance reading of 0. So things are backwards if what's bigger than what? If
P is bigger than P naught.
P is bigger than P naught. But it's easier to think of it as P naught being too small. You screwed up. That's what it means. Your background is absorbing too much. It's attenuating. It's not a true background. You screwed up. Your background is just absorbing too much. Okay? So, and it happens a lot. So why not just what is the most reproducible background that can be used in an absorbance measurement? Nothing. Why have a cuvette sitting over there? There's no point. Why have a cuvette filled with water? Just chance for error is all it is. Right? Just have nothing. That's the most reproducible. Right? Yeah. Now, there is a time when you'd want to put something in the reference cell. Right? Let's say you're looking for some dye that's just killing all the little fishies in Elmendorf, right? And this dye, it's way on the blue region, right? Because I don't know if the absorbance spectrum of water really skyrockets, goes way up in the ultraviolet. Water absorbs UV really well. So maybe this little dye and water absorb in the UV region. Well, if you have air as your background, all you're going to see is absorbance spectrum of water. You're not going to see your little dye or your little enzyme, whatever you're looking for, right? So you put in water, and that's the only time, really, where you go through the work of putting something in the reference cell, is when your background absorbs where your sample is interested in. And the result is kind of noisy, but at least you get something, okay? You can subtract it out. Why do red dye molecules, or what do red dye molecules do to make a solution appear red, Anna? The hint is the color wheel. What do red dye molecules do to make a solution appear red? How does the color wheel work? There's no artists in here? I don't know if artists even really care about this because they just do it by experience and practice.
Use the primary colors and then you mix them together, like blue and yellow.
Yeah.
And you get green, and then you mix green with
yeah,
yellow,
they're
and you get yellow, green.
But they're not. Yeah. So it's more practical. So I don't know. Artists would really be the answer. But color wheel. All you do is you go across And you see, oh, you remove this. You remove this. And you see more of this. So you're Andy's shirt. Her little dye molecules are really heavily absorbing this region of the spectrum. And her shirt appears red. If you want your shirt to appear yellow, you need little dye molecules to heavily absorb this region. Okay. That makes sense?
So then the red has to absorb the blue green.
Yeah, that heavily absorb that region. You know, absorbance is really kind of ugly and messy. It's kind of like a blob. So it's going to be this general region. So you need to absorb. Yeah, exactly. It's well, think of it this way. It's absorbing the blue, reflecting everything else. Everything else has to be there, but everything else is there. So we're talking about sunlight, white light. Everything is there. We're just removing the bluish-greenish area to make it really appear red-orange. Okay. Why is a white T-shirt so much fresher than a black T-shirt? Fresher. Fresher. Fresher is hip? That's another word for hip? No, fresher. It feels better. Yeah. White is reflecting all of them, right? White is reflecting all the colors, right? It's not. Is it absorbing anything? No. At least not in Roy G. Biv. It's not. Okay.
Oh, okay.
Black. It's black because absorbs Roy G. Biv. Every single one, right? In the visible spectrum. Oh, that's it.
So yellow would absorb the light?
Well,
Anything else?
it's, I don't know if it's perfectly violet, but it's going to be that, definitely violet would be in the center of it, that blob in that region.
Pretty much whatever.
It's like opposite blob.
Yeah, it's
Yeah.
not yeah.
But it would be I think it'd be very safe to say, Pablo, yeah, get rid of the violet. It'll appear really yellow.